Very well, good morning, good afternoon, good evening, wherever you are in the world. I know we have participants from all time zones present at our session. This is about another fascinating pollutant that are the chlorinated compounds. Compounds that bother us a lot. We found them often in soils and they're quite difficult to assess. Parts of the chlorinated compounds are the DNAPLs, another very interesting feature of the chlorinated compounds. This session got a subtitle, the nice subtitle, Optimize the Process to Achieve the Target. We have 7 speakers. It looks like a very interesting program to me. I look forward to it. We have 3 chairmen. We will introduce ourselves. I will begin with myself. I'm Frank Zwartjes from the Netherlands. I work for 35 years now in the field of soil pollution. I more or less covered all aspects, but my favorite is risk assessment. For now, the last 30 years, I've been employed by the National Institute for Public Health and the Environment. Christiane, would you be so kind to introduce yourself?
Yes, thank you, Frank. Good morning, good afternoon to everybody. I'm very pleased to co-chair this session this morning. I'm Christiane Vermeij. I've been working for the Swiss Federal Office for the Environment. I'm the head of the section Contaminated Site in the Federal Office for the Environment.
Thank you very much, Christiane. And then we have a very experienced soil pollution expert from Australia, Professor Ravi Naidu. Ravi, would you be so kind to give a short introduction of yourself?
Thank you very much, Frank, and good morning, participants. I'm delighted to be one of the co-chairs of this session. Like Frank, I've been working on pollutants for just over 30 years now. Both inorganic and organic pollutants. And right now, I lead CRC CARE, which is Cooperative Research Center for Contamination Assessment and Remediation of the Environment. It's a Australian Center of Excellence and brings together a number of participants, including the Department of Defense, answers 50%, and we have mining companies and collaboration with EPAs as well. I do look forward to this session. Thank you.
Thank you very much, Ravi. Some rules of the game you probably know by now. We do not have Q&As after the presentations. We do have a discussion part at the end of the session. That is only 10 minutes at most. So I propose when you have general questions or observations to put them on the chat. If you have very detailed questions, maybe it is better to address the authors directly. All presenters have their email addresses at the end of the presentations. So we invite you to put your questions on the chat, but please stick to more general questions. Like yesterday, we had dozens of questions and only 7 minutes to answer 2 of them. So that doesn't make sense. Okay, let's start. I give it over to Christiane, who will lead us through the first part of the session. Christiane, please, the floor is yours for the moment.
Thank you, Frank. So I have the pleasure to introduce our first speaker of this session, who is Mariangela Donati. Mariangela is District Manager for France, Italy, and other Mediterranean countries at Regenesis. Since 2019, she is responsible for all sales and customer support across the Mediterranean region and provides business development in her district. Mariangela will present us a project about the integration between in-situ sorption and ICCR to optimize treatment timeline for a PCE plume. Please, Mariangela.
Thank you. Good morning. Good morning, everyone. I'll share my screen. Okay. Now you should see in the presenter mode. So yes, I will present you today a case study on an in situ treatment with sorption and chemical reduction on a PCE plume. I take the occasion to thank Alessandro Lucchesini from CECAM that provided us the data and allowed us to present his results. Let's start from the beginning. I will show you at the beginning the context of the application. We are in Florence on a former industrial site, a former production of frames. On site, the site is under redevelopment for residential use. We have an aquifer with very fast seepage velocity, and the main contaminants are PCE and TCE, but we have also daughter compounds like vinyl chloride and DCE. The concentration are lower than the target inside the site. The target inside the site is the CSR is a target that is in the Italian regulation is a risk-based. These are risk-based targets. The objective of this treatment was to reach lower targets that were at the site boundary, called the CSC in the Italian regulation, and these are table limits, so they're not calculated and they're not risk-based. We were in very demanding condition because there were very strict objectives. First of all, there was a need to have very quick results in order to have the maximum return of the investment. While the remediation was ongoing, there was also the construction going on parallel. So we need to interfere at minimum with the construction activities. There was, of course, a need to have a long-term treatment, even if there wasn't a direct, there hasn't been a direct treatment of the source. And most of all, we had very demanding targets at the site boundaries. For example, for vinyl chloride, we had to reach 0.5 microgram liters. So to achieve this demanding target, we propose to inject a permeable reactive barrier where the key, where the key reactant used was plume stock. It's a colloidal activated carbon that allows us to have very rapid results and at the same time to have stable results, to have a remediation that work really on the long term, and also to achieve very low target. As per every case where we have a permeable reactive barrier, and in particular in this case where we had a very demanding condition, it is very important to know very well the site, the contamination, the hydrogeology. So we proposed to do some DVTs and remedial investigation additional to what was in the characterization. For example, there was some PFM, some passive flow meters were installed in order to measure directly the mass flux, and that provided us from some very interesting results for the design of the remediation. For example, we measured a very high flux, and we observed that the contaminant flux was very similar at every depth of the aquifer. So we didn't need to change, for example, the dose of reactant at different depth. This is the layout of the remediation. We injected a barrier of 25-meter length. Here you see the two compliancy monitoring well down gradient to barrier. We treated with the injection a layer of 8 meters, and the main technologies we used worked on sorption and chemical reduction. This in order to minimize the production of daughter compounds from TCE and TCE, and in order to have quick results. So what are the reactants that we used? plume stop, it's the colloidal activated carbon that has been injected. To create plume stop, we milled the activated carbon in order to have something that distributes widely in the aquifer. In order to have a sort of, with injection of plume stop, it's like that we create a purifying filter directly in the aquifer that acts very rapidly. At the same time, the contaminants sorbed to plume stop are bioavailable and can be degraded. So how it works, we inject plume stop, it fixed to the solid matrix of the aquifer. The contaminant in the dissolved phase sorbs on the sorption side of plume stop of the activated carbon, but they are anyway bioavailable, so they are biodegraded. And in this case, we added 0 valent iron in order to have also a chemical reduction of the contaminant sorbed. The chemical reduction and the biodegradation allow us to regenerate the sorption site of the activated carbon in order to have new sites to sorb new contaminants. So we have a very long treatment thanks to the self-regenerating capability of plume stop. As micro-CVI is the 0 valent iron that we used. It's again a colloidal reactant, so it's very easy to inject, and it allows us, together with plume stop, to minimize the production of daughter products from the degradation. In this case, adding to the sorption, adding the process of chemical reduction, of direct extraction of the daughter compound and of the parent compound. And it allows us also to regenerate the plume stop, destroying the compound. So how it works, the dissolved phase contaminant, for example, the chlorinated solvents, are sorbed onto the particle of 0 valent iron, and then they're electrochemically reduced. In this case, in this plume, we also had, we didn't have only PC and TC, we had also already daughter compounds before the injection. So we decided to work not only on sorption and chemical reduction, but also to enhance the biodegradation in order to be sure to get to the complete degradation of the daughter compounds either and rapidly. So we also applied the nitrogen release compound, HRC, and the BDI, that it's an inoculum, it contains natural occurring microorganisms. So now you see some picture from the side, and like this, you will have an idea of the disturbance that was inside. So the place we need was the place for the mixing activities, the place for the geoprop to inject by direct push, and the space for the stock of the product. Concerning the post-injection monitoring, not only the contaminants were measured, but also other parameters that provide us information on the evolution of the degradation. And now we can see some results. So we have seen that there were two compliance monitoring well done within the barrier. I will show you only one of them, just to don't lose too much time. I will show you anyway the worst one, the one that was more contaminated, and also the one for which we have more historical data, because the other one has been realized just before the injection. So we had only the only one campaign before injection. So here you see the result for concerning the parent compounds, PC and TC. So the injection were in the summer of 2020, last year. And we see, here you see the remediation target at site boundaries for PC and TC. And already after 1 month, we reach this target and we have stable results also on time. After the 6 months, we are under the detection limits for both contaminants. So these rapid results are possible thanks to the combination of sorption and chemical reduction. These processes works very fast on this contaminant. They are a little slower on the daughter compounds, like we'll see here. So here you see the concentration on time for DCE and vinyl chloride. The degradation process is a little slower, but I remind you that they were already present before the injection of our reactants. And even if we see it slower, we see for DCE was already under the concentration, the target of concentration, but we see a reduction of 1 order of magnitude after 3 months. For vinyl chloride, it's less evident, but after 8 months, we are under the target of 0.5 micrograms. So this is also the effect of the combination of this approach that allows us to reduce the formation, the creation of daughter product while degrading the parent compound that we just saw. So just to summarize, this permeable reactive barrier with a reactant that can be injected allows us to have a very quick reduction of contaminants with a minimal disturbance on site that allows to go on with constructions and that allow to have nothing left on site after the remediation. It provided a long-term protection, minimizing the daughter products, and we are getting soon to site closure. So after a little more than a year from the application, we are getting to site closure. We had the first post-compliance validation campaign last June, and the next one will be end of the year. So I finished. Thank you for your attention, and talk to you later for your question.
Thank you very much, Mariangela Donati, for this very interesting presentation of this case study. I go forward to the next speaker. So the next speaker is Pierrot Mori. He is a partner and the technical responsible for site remediation of ERM in Italy, with over 30 years experience in contaminated sites management. Pierrot Mori is a specialist of in-situ remediation through innovative technologies. He has managed for multinational clients complex program of soil groundwater assessment remediation at industrial and brownfield sites. Pierrot Mori will present us now another type of in-situ remediation technique with a heating project. Please, Pierrot Mori.
Okay, do you see the screen?
Yes, can you put in a presentation mode, please?
Okay.
Thank you very much.
Work, okay. Thank you very much, and good morning or good afternoon to everybody. So I'm going to speak about a project that we almost completed in northern Italy that is based chlorinated remediation based on heating technology, electrical resistance heating in particular. It was performed as at an active site, so industrial site that was in operation. I will speak about the technology and then in general, and then about the specific project in terms of design, performance, and results. Few information about the technology. So first of all, what is thermal remediation? It is a technology that, I mean, there are several technologies that via the heating the subsoil, they can remediate several chemicals in soil and groundwater. It can be applied to, in these particular cases, to chlorinated solvents, but there is a wide set of contaminants that can be addressed by these technologies. And there are mainly 4 technologies: steam enhanced extraction, electrical resistance, the one used at this project, thermal conductive heating, and radio frequency. So I would I won't go so much in detail in the different technologies. I will speak about what is the ERM approach to this kind of technology. So this is the main point of the approach is that it must be based on a very detailed conceptual model. So high resolution investigation have to be applied at the site. And also they can be used in a framework of a life cycle assessment of a remediation project. And the use of particular modeling, thermal modeling software that has to be used. And also above all, I would say the hazard evaluation of the threat, especially in case we are working at an active site. So any kind of interference with the people that is working and the structure have to be analyzed in detail. This kind of technology can provide significant benefits because I can mention that it works I would say, independently of variation of lithology. So we can work with success both in fracture bedrock and also in clay. Clay was the case we are going to show. This is the main point that I would like to stress. Then we can mention that there is a high percentage of reduction and with very limited risk of rebound. It is I would say, an aggressive technology that can provide results in a short time frame. Another point to mention is that the technology itself has a significant cost, but in the end, compared with other technology like a classical pump and treat, you can see from this graph that you have an initial cost that is definitely higher, but then you can meet and you can complete a project in terms of months. So that is very different compared to other technologies like pump and treat. So the overall cost can be lower. About electrical resisting heating. So we are heating the subsoil through the passage of electric current. And then we reach the temperature that can volatilize the contaminants. And so the contaminants are going to be recovered in the vapor phase. This is the main principle. The applicability of this kind of technology is shown in this graph. So you can see that applicability is both in the unsaturated layer and in the saturated layer, and it can be applied to clay soils where you have very low permeability and you can encounter very significant problems in addressing the contamination with the traditional technologies. Even with injections of chemicals, you may have the problem of delivering of the chemicals. There are many types of this technology. They are from different providers. In this case study, we refer to ETDSP that is provided from McKillian McGee Corporation in Canada. So they were the provider of the technology for this site. Regarding remediation design, the contamination was from mainly several chlorinated ethylenes, but mainly tetrachloroethylene in the unsaturated and saturated layer with very high concentration, especially in groundwater, that is a few meters below grade. As said before, we completed an accurate source zone delineation using MIP, so high resolution, to give a very detailed 3D reconstruction of the contamination that is shown here. So in the end, we reconstructed that 64% of the total contaminated volume, saturated and unsaturated, was in clay. And so this was the main driver of the selection of the technology, because it was very difficult, something that is very difficult to address. This technology was proved to be effective in clay, in fact. In terms of depth, the maximum depth reached by the technology, as shown here, was 12 meters, but the treatment zone was agreed with authority to be from 4 to 7 meters. So we were allowed to leave the deeper contamination as it was considered immobile. So we started the design with the thermal modeling on the basis of the data that were already available. And then we designed a multi-phase extraction through a multi-phase extraction pilot test, the extraction system. Another point that was very important in the design phase was subsurface utility mapping and management through cooling systems that were designed for the underground utilities or were not possible to install a cooling system, relocation of some of them. Also, another point was that we monitored the geotechnical reaction of the soil. So in the design phase, that was considered to prevent any kind of settlement of the soil due to heating. This is the layout of the system compared to the distribution of the contamination. You can see co-located electrodes that were the one that were used to heat the soil through the passage of electricity, and that were co-located with the recovery points with the multi-phase extraction system. Also, the recovery was through also horizontal vapor recovery lines, and you see also the temperature monitoring sensor that were used for the reconstruction of the temperature in the subsoil. This is the map and the layout of the system with the different units. You can see also a photograph during the installation. So there was a powered unit delivery system connection with the transformer of the energy provider. Then there is the other important point is the extraction system and the treatment system of water and vapors. Here you can see a scheme of the electrodes on the right. You can see there is the boreholes filled with granular materials, and the two electrodes that were inserted in the same boring, that is as well the electrode, but also an extraction point for the recovery of the contaminant. So going to the performance, I show here the heating performance so the target concentration was 88 degrees. That was the boiling temperature of tetrachloroethylene and the initial PC poor phase water interface. So we reached as average, we exceeded that and what reached at most of the point, even if some of the point did not reach the target because of logistic constraint in the distance of the electrodes. And here is shown the heating performance of the system. So we didn't reach at all location the temperature because of sometimes the distance between electrodes had to be increased because of logistics. Here is you can see the recover graph. So that shows the time frame of the project. So during the heating and the curve of recovery compared to the rate, so the recovery mass rate during. So in the end, we recovered 500 kilograms in 7 months. That was absolutely as was the forecast during the design phase. So we reach asymptotic condition after 7 months, and we stop the system. After the stop of the system, we made interim sampling to check what were the results. Then now at present, the monitoring, groundwater monitoring is still ongoing. But it's interesting to show the results of this interim sampling, because we can show a very significant decrease at the same location. So here we show a pre-remediation, the post-remediation results at different locations. And you can see that there are very significant reduction where it is comparable. For example, here where you can see a reduction between 175,000 to 400, for example, in groundwater. But so also in soil and groundwater, we had at several points a very significant decrease. Even if at some location we weren't able to reach the very low required concentration that are set for target. So as a conclusion, we carried out this full-scale program using 60 electrodes at 38 locations. And so we are very close to close this procedure with the result of 500 kilograms recovered, and with a reduction that exceeded 99% in this short time frame that we mentioned. So we think that this technology has been proved to be a valid source treatment to enable more rapid closure and remove longer term remediation costs. And the work, this is very important, was completed safely without any business interruption at the site, without any excavation and without any interference with the work carried out on site. So this is the end of the presentation. Thank you very much, and I'm available for any question after.
Thank you very much, Pierrot Mori, for this very interesting presentation on this project. I will present now our next speaker, who is Valeureux Illy. Valeureux Illy is a PhD student at Bordeaux INP. His current research focuses on how one can discriminate between sources of groundwater pollutants by using historical information, hydrodynamic and chemical data. Valeureux Illy, can you please share your screen?
Yes. Can you see the screen, please?
We can see the screen, and you only have to put it on the presentation modus.
I think it's good now. Is it?
No, yes. We see the presentation, but not in presentation modus. Sometimes it's better to do that a second time.
Yeah, I retry again and wait for a few seconds. Still not?
Not.
Oh, let me try again. I can see that. Yeah, if you don't, but if I change the slide, can you see it or not?
Can you share your screen? We don't see your screen anymore now.
Because I see on my screen something.
André, we did see your screen a minute ago. So when you share it again, I think it will work.
Okay.
Yes, now we see your screen.
Okay, full mode now.
Yes.
Yes.
We see the slide, but not in the presentation modus.
What is happening? Cannot understand this. Arrêtez le partage.
You have try perhaps to put in the presentation modus and then to share your screen.
Okay.
And if it doesn't work, we go on with the presentation.
Share screen option. Participant all participants. Okay. Good. I'm very sorry, but I don't see how to make it better. New share. Fenêtre, écran.
We could continue.
Yeah, we can go on with.
Yeah. Okay. Yeah, I shared it, but I don't know why you cannot see it. Maybe you can take the next person, and I will wait for the, I don't know.
Perhaps can you share as it was before, and we go on not in the presentation modus, but we can see your slide at least.
Yeah, because right now, for example, I see something loading, but I don't know why it's still turning around. I try it again, but
and then we go on.
Yeah. Tout l'écran. Fenêtre onglet. Yeah.
So we go on with the presentation, so it's okay.
It's fine
it's
like
okay?
this.
Yeah, yes, we go on
fine.
like this.
Okay,
Thank
I'm
you.
gonna do it. Yeah. So if I change the slide, you can see it.
Yes.
Okay.
Yeah.
So I'm
We
gonna
see the
do it
second
like
slide
that.
now.
Yeah. Okay. All right.
Thank you.
So I'm very sorry for that. So what I'm going to present today is how you can use trichloroethane to understand transport of contaminant at real sites. So why you can do this is because for trichloroethane, which I will call TCA for short, under aerobic conditions, you have in the scientific literature some data about the kinetics that you can use to try to understand more about the contamination. So the objective of my study, this specific study, is to use these data to understand the origin of the contamination, and also try to anticipate the future concentration in the groundwater. So first, what I'm going to do is to present to you the site. So it's an industrial plant with this plant, in fact, is a automobile manufacturing plant where they have used this compound in the past for degreasing the metal parts. And as a consequence of this usage, we had a contamination in the groundwater for long ago, but still we have concentration on the water. So here I present to you the geological map, and the red contour is for the site. And in fact, so the site rests on a silt and flint residues, which itself rests on the chalk aquifer. So I will remove this map. So here you have the flow pattern at the level of the site. And I try to, can you still see it? Yeah.
Yes, we can see it. Thank you.
Okay, so here you have the flow and the piezometers locations, and also area of contamination. We do not really know the exact location of the sources, but it's relatively well known. So the model is going to suppose that the distance from the piezometer and the sources is about 150 meters. And so we have on these two piezometers the concentration of TCA and its degradation product, which is the 11-DCE. So this concentration time series is almost 20 years long, as you can see, and we have different peaks over time of different shapes. So the question is, why do you have these different peaks? And what we wanted to do is to use, like I said before, the degradation kinetics to try to answer these questions. So I give here some references for studies that gave the kinetics and also the yield of DCA, which is very important for this kind of study. So if we do that, we were able to go back to the origin of the contamination on both piezometers. And so it gave us the year 1990 as the origin of the contamination on both piezometer, with a little difference of a few months. So, okay. Also, we have made some analysis on the geochemistry of the groundwater, and this showed dissolved oxygen level between 1 and 10 milligrams per liter, and redox potential between 100 and 220 millivolts. So basically, the groundwater condition is aerobic, which allow us to use the kinetics of these papers. So now for the model, what we did is we tried to find different elementary model that could help us to understand what is going on. So this is the different hypotheses that we have done. And as you can see, for example, if we suppose that the source of the contaminant is a DNAPL in a very homogeneous medium, we get this concentration breakthrough that did not fit the data on the piezometers. So that this model cannot work. So now I'm going to present to you the other models, what they gave. So the first one is when you suppose that the source is entirely dissolved in the groundwater. In this case, you have the first peak, which is relatively well fitted, but the second peak and the tail of the concentration, which is very important for the site managers to understand what's happening. We can see that with this model, we cannot fit the tail of the low concentration ever. So the second model, we suppose now that we have a dual porosity medium, and this is really a very old way of modeling very highly heterogeneous medium where you have fractures and others. You can do it by this model, for example. And the reference, I didn't give it here, but it is by Jean, I think the name. So if you do that, you can see that the tail, you can start now to fit it, but the second peak and still the take is not very well modeled. So the next model we did is to now suppose that the source of the contamination is in a heterogeneous zone. So you have a part of it which is in a very high, let's say, hydraulic conductivity zone, and the other part which is in a very low hydraulic conductivity zone. When you do that, you can see that Now you can model the low concentrations, but it depends whether or not you put DNAPL in the source or not. If you put DNAPL, you can also have a fit of the ratio of DCA over TCA, so which is quite good, let's say. Now the final model, what we do is we suppose that we have two contamination that occur in time. Say the first one and the second one a few years later. When you do that, of course, you can see that this is the only way you can fit the first and the second peak. So I want to make it clear that all these models, we were not trying to have a very complete model. We were trying to see different, let's say, small models, and we know that by doing that we can learn things about the site. So it may be that in reality what's happening on the site is really a combination of different our different models here.
Valerie,
yeah.
I'm sorry to interrupt you, but we have to keep time. May I ask you to accelerate and
this is my final. Right, this is my final one. Okay, so
because the presentation doesn't go on. We always see the third slide. Yeah. Okay.
Oh, okay. So
thank you. I'm sorry.
Okay. All right. So to conclude, we were able this way to go back to determine the origin of the contamination, and also to have an understanding of what is going on in the site. So thank you very much, and very sorry for the trouble.
Thank you very much, Valerie. I'm also sorry to interrupt you, and I'm sure that will be some questions about your interesting topics at the end of the session. So now I let the floor to Hadi. I'm sorry, some people are speaking. Can you all put your microphone on mute?
ఎవరో తెలుగులో పెట్టి దిస్ ఈజ్ మై మదర్ టంగ్ బ్రదర్ అని మనం పెట్టాడు ఒకటి. దిస్ ఈజ్ మై మదర్ టంగ్, ఐ స్పీక్ దిస్ లాంగ్వేజ్.
Javi, can I let you now the floor? Thank you. Javi, we don't hear you. Now it's okay.
Christian, Frank, we cannot hear.
Yes, Ravi, can you present the next speaker, or do you want that I present him?
You started, Christiane, you can present this, and then Ravi takes over the next speaker.
Yes, yes,
Thanks
of
so
course,
much.
yes. I can with pleasure present our next speaker. He's Mike Muller, and from Paroxychem Environmental Solutions, and he will present us a project of sodium persulfate with integrated activator destroys up to 99% of trichloroethylene in 5 weeks at a manufacturing facility in the Netherlands. Please, Mike Muller.
Yes, good afternoon. I presume you can hear me.
Yes.
Just one final check. Thank you. Good afternoon, and thank you for participating in this presentation today. My name is Mike Muller, representing Paroxychem soil and groundwater remediation team here in Europe. And today we'll be looking at a recent case study in the Netherlands where one of our persulfate-based ISCO technologies was used to treat TC impacts in an urban center aquifer. This does not advance. Yeah. Sorry. Here we go. Just a brief introduction of the company. We were recently acquired by Germany-based chemicals conglomerate Evonik. Paroxychem has a broad and growing portfolio of both in situ and ex situ remediation technologies, as summarized here in this table. So whether your contaminant profile would best be treatable with ISCO, ISCR, aerobic bio, anaerobic bio, stabilization, etc. Because of this, we are often able to assist clients in determining some viable options for a contaminated site based on their budget, speed to cleanup, or other site constraints. And today's case study will be focusing on the Closure 1 ISCO technology highlighted there. My presentation will provide some details on the technology itself, followed by the case study. I have provided relevant contact details at the end of the presentation. If you have any questions, would like a copy, or later opportunity to discuss the technology in more detail. For those of you who are here, we have an exhibition booth in Ferrara, and it would be nice to have you visit if possible. As you may already know, persulfate should always be activated prior to any field application. The most common approach used by clients is alkaline activation, typically in the form of NaOH for groundwater applications, and hydrated lime for soil mixing applications. Heat is increasingly being used, particularly as part of a thermal treatment strategy. In fact, we currently have a large project underway in Gela, Sicily, in partnership with the company Hammers Technology. We spoke about that this morning. Hydrogen peroxide activation, it's a powerful approach with its own place in the hierarchy. And lastly, transition metals activation, which is what this case study will explain in some more detail. So what is Closure 1? It is a blend of 95% Closure SP sodium persulfate with 5% of an activator blend included in the same packaging. It was designed to be a convenient and easy to use formulation of activated sodium persulfate. And this combination can simplify ISCO project design by allowing a single injection solution requiring just a single tank to batch the reagents, thus a simplified field injection process. It's a fully soluble all-in-one product. Each of the components are easily mixed in water. Some of the key characteristics of the product are that it is firstly stable in the bag, and that it's classified as a UN 5.1 oxidizer, which is the same classification as sodium persulfate. Thus, it can be handled in exactly the same way as standard SP, including transportation and storage requirements. It is soluble once batched and will stay in solution for the 2 to 4 hours within which we recommend batches be injected. It can then be used to aggressively treat your target contaminants of concern. A few other characteristics worth mentioning are that Closure 1 contains a built-in pH buffer to help maintain near neutral pH, and that the product has multiple activation methods combined into the single blend. So this is actually what Closure 1 looks like. For anyone who has implemented activated Closure ISCO technologies before, you're going to notice that it is a different color. Closure SP tends to be a very clear solution. This, of course, is purple. The reason it has a pink to purple color is due to the fact that Closure 1 contains some potassium permanganate in the blend. We do not anticipate nor intend for this color to persist in the subsurface. to actually activate the sodium persulfate, we will want the more reduced oxidative states of manganese 7 to manganese 5 and so on. Thus, the initial solution is going to be pink to purple. But here you can also see, though, that the dry phase is an off-white powder, some darker specks mixed throughout. So what are the activation chemistries within closure one? We have iron, chelate, and manganese included in the formulation. Both iron and manganese are transition metals and cycle between oxidation states. And it's the reduced oxidation states that activate the persulfate. As you will know, permanganate is actually manganese 7. And as the oxidation state of the manganese changes, the color of the solution will change, and manganese can serve as a second transition metal to activate the necessary persulfate radicals. We added these different transition metals to essentially build a little redundancy into the system, thinking that in some situations, iron might serve as a better activator, and in other situations, the manganese may. Because this is a transition metal activation system, it is primarily generating the oxidative pathway as opposed to the reductive pathway. You're primarily getting sulfate or hydroxyl radicals as the species which are going to do the most damage in treating your contaminants of concern. This means that closure one is primarily aimed at treating compounds like TPHs, but it can also be used to treat chlorinated ethenes, chlorobenzenes, and specialty compounds such as the recently classified emerging contaminant 1,4-dioxane. Basically, this is just a partial list. Anything that can be oxidized, we expect closure one to be able to degrade. In terms of materials compatibility, we want to emphasize that closure one is very similar in corrosivity to iron chelate activated sodium persulfate, and that it does react with carbon steel. And this is relevant because carbon steel is used to manufacture a lot of the DPT rods people use to inject reagents and in soil mixing equipment. There are specialized DPT rods that are made out of stainless steel or have some sort of stinger that goes down past the carbon steel component to prevent contact. The main takeaway is that if you are planning to deploy carbon steel components, you will want to plan for some way to protect them or switching over to some sort of compatible material such as stainless steel. For soil mixing applications, you can always use classic alkaline activated persulfate, which has been injected through carbon steel DPT rods. This is practical because high pH associated with alkaline activated persulfate does tend to protect carbon steel. One of the main advantages of closure one is in terms of batching. You can use a single pump to pump whatever you batch into the ground because you no longer need to have dilution water, or you don't have to do inline mixing and blending of the different activators with sodium persulfate. One of the advantages now is that you can literally batch at your injection concentration. So if a design engineer is located in an office far away from the site, instructions can be relayed to the field workers indicating the preferred grams per liter mixture, and they would simply batch at that concentration. We recommend the product to be injected within 2 to 4 hours of batching. Not that we expect anything bad to happen if the solution sits longer, but this guideline has been identified as a best practice to follow in the field. In terms of the time it takes to dissolve the product, since all of the components are highly soluble, they dissolve quickly. We expect a 5 to 10 minute time frame, with lower concentrations generally requiring less time and higher concentrations a little longer. It really depends on how good of a mixing system you have. And of course, even with the appropriate mixing and batching systems, chemically compatible equipment is recommended. Tanks, pumps, gaskets, pressure valves, flow meters, and any wetted parts should be chemically compatible. Moving along now to the actual case study. Our primary liaison partner was the Dutch contracting firm Heijmans. For several years, a manufacturing facility was in operation near downtown Uden in the Netherlands. And as a result of business activities at the site, soil and groundwater were impacted with chlorinated hydrocarbons, especially TCE. Following demolition of the buildings in 2005, a detailed site investigation revealed fairly high contamination levels. In the groundwater aquifer, concentrations of over 14 micrograms per liter of trichloroethylene were measured, indicating the presence of a source zone. And the impacted source zone was 270 square meters contaminated in the saturated zone from 3 to 7 meters below ground surface level. For planned redevelopment of the site into residential area, the local regulatory authorities, as is usual, mandated remediation to their fairly stringent cleanup target levels. Following the SI, as per standard operating procedure, the first phase was excavation of contaminated soil to the top of the groundwater level. This was followed by backfilling the area with certificated clean soils. Since the envisioned end use again was by a real estate developer for residential housing, rapid results were required. Key elements of the remedial options appraisal process included selection of a technology solution that provides firstly high reliability, cost-effective implementation, and quick treatment results. As is typical in the Netherlands, the engineering consultants conducted the SI and were involved with results verification, whereas the lead contractor was responsible for overall project management, including influence on technology selection. Again, the Cisco technology was selected primarily because it met all the ROA objectives. The blend of sodium persulfate with built-in activation chemistry provided powerful oxidation capacity as a ready-to-use product suitable for this highly contaminated treatment area. A total of 9,225 kilograms was required, delivered in 25 kilo bags from a nearby warehouse, helping to keep the logistics carbon footprint low. As persulfate does require careful handling, the contractor did take all necessary safety measures for storage and handling. Factors such as fire safety and unpredictable summer weather also played a role here. From the storage facility, the product was transported to an on-site mixing facility. There, the bags were opened under controlled conditions to ensure little physical contact between field technicians and the sodium persulfate itself. Special attention was focused on reducing the production of any dust particles. The injections were made per batch, as outlined in Figure 1, and in the injection plan, there were several different concentration batches provided. A typical batch contained 4 cubic meters of clean water, into which a specified amount of closure 1 was added. And from the mixing unit, the proper solution was then transferred into the injection tank. As each batch of injectable solution is mixed together, it's then applied to the subsurface through existing injection wells. In total, the contractor used 40 injection points at 3 different subsurface levels in a grid pattern with a center-to-center distance of 2 meters, as seen here in Figure 2. With this grid, it was possible to engineer contact across the entire source area, which is always an important factor in ISCO applications. At spots with higher concentrations of contaminant, more solution was applied with a higher concentration of persulfate. At each injection point, about 2,775 and 4,500 liters of solution were applied. Through the use of a manifold system, here's a photo of it in Figure 3, 4 to 6 wells were worked simultaneously, using a little overpressure to prevent blowout at the surface. Before actually starting the injections, there was a reconfirmation of on-site TCE concentrations, revealing persistently high levels as originally detected. Monitoring activities during and after the injections primarily addressed measurements of pH, oxygen, redox, and electrical conductivity. Following the injections with sodium persulfate, there was a notable and expected decrease in pH and an increase in electrical conductivity detected. Contractor used our field test kits. Here's a photo in Figure 4 to provide indications of the actual amount of active sodium persulfate still available in the system. The key parameters were monitored weekly, and after 4 weeks, most of the persulfate was consumed. Monitoring was conducted through 10 wells. TCE concentrations decreased to below the target levels in all of them. And 1 month later, an independent verification by the engineering consultants reconfirmed these positive results. They also concluded that there was no active sodium persulfate left in the system and that the TCE was sufficiently removed. The final results summarized here in Table 1. So in total, the ISCO process removed over 99% of the TCE pollution, and with these results, the client and the regulator accepted closure of the site with no further remediation requirements, and there are some nice apartments there now. So to briefly summarize then, Closure 1 is a single product where Closure SP sodium persulfate has been combined with the activation chemistry, and the intent of this is to have a blend which uses just a single tank, a single injection system, and where the designers only need to come up with a single design number for the overall system so that you can have a very simplified ISCO application. Thank you very much for your attention. I do believe Mr. Opdam is on the call. And so when we come to questions, if there's anything that is more appropriate for him, he's available. Thank you very much.
Thank you very much for this very interesting presentation. And I let now Ravi present the next speaker.
Thanks. Thank you very much, Christian. Mike, would you stop sharing?
Yes, just a moment, please. Sorry.
Thank you. Our next presentation is by Dr. Craig Cox, who is from Cox Calvin and Associates, and Craig is President and Principal Scientist with this company. Craig's presentation will focus on successful closures of DNAPL site lessons learned. Over to you, Craig.
There is no sound.
Craig, can you speak?
All right, sorry about that. I'd like to start off by going through some, what my talk's going to be about. So there, I want to touch briefly on some guidance, some reference documents, the approach we used at this site, then some tools and techniques, and some of the keys we found that led to the success for this. So some of the key guidance, there was guidance put out in 2003, the DNAPL remediation challenge by US EPA, where they asked, does pump and treat really work? And came to the conclusion that it doesn't, and that you really need to address sources. So that's a key one to look at. The next one is DNAPL remediation selected projects approaching regulatory closure the following year by US EPA, where they basically kind of threw in the towel and said, we probably will not, reach sort of the goals that we want for uncontaminated groundwater at DNAPL sites. So we have to come up with some other approaches. In 2007, then, US EPA came out with a document that was recommendations based on the groundwater conditions at both sites. And then Appendix A of that document is where they came up with the idea of alternative concentration screening levels for DNAPL sites. And so that was a very important document. If you can get a hold of that, take a look at it. I looked today online, it is available. Then in 2011, ITRC came out with guidance that kind of put all this together with approaches for looking at DNAPL sites and how to remediate them. There's a couple of good references that you still can get a hold of that'll be important. The first one is Cohen and Mercer in 1993, which is DNAPL site evaluation. Still a very good source for information. It's a pretty easy read, actually. Then in 2014, there was a chlorinated solvent source zone remediation that was prepared, and that one really kind of ties the whole thing together. But it's a hefty book. It's a tough one to get through. You really have to love DNAPL sites to go through that book, but it's out there, and it's a very, very good reference. So our approach to closure at this site was first to reduce the immediate risk. So if you eliminate and reduce risks at the front end, it helps you with the back end, gives you more time. Then we developed a detailed conceptual site model. And at that point, we started to work with our regulators so that we could come up with a path forward that would establish realistic goals. Then we reduced the source strength to below soil saturation concentrations. At that point, we realized we were going to have to evaluate and incorporate activity and use limitations. So that was going to be a key element in the success, was you were going to just basically say, the groundwater beneath the site cannot be used for any purpose. And then we went into a long-term monitoring phase. So the tools that we used, we did use high-resolution site characterization. Everybody should probably approach it in that way with soil gas surveys. We use membrane interface probe. hydraulic profiling, and dye laser fluorescence. Now at this site, we weren't able to do that because a lot of those tools weren't available then, but we did use the MIP. Then the next important part is documenting the mass reduction. So you have to quantify, this is probably the hardest step, is quantifying the pre-remedial mass. So how much mass was in place and how much can you destroy? And so quantify the mass removal that comes from every media that you treat. So if you have air streams that come out of SVE systems, monitor the concentration of those streams so you can calculate what the mass is. If you have produced liquids, you can understand how to get the mass out of those pretty easily. If you excavate media, understand how much of the mass you excavated there. And then in situ destruction, that's the hardest one to estimate because there's no real good way to estimate what the destruction actually was. You can calculate what you think might happen, but it's hard to actually come up with a hard number. So the keys to success: eliminate or reduce primary risk drivers as soon as possible, work closely with regulators to develop realistic goals, and with the clients, and develop a high resolution data set to revise your CSM accordingly, and finally, document mass removal. So here we'll take a quick look through a case study. This site was a specialty metal recycler in central Ohio, and they received cuttings from machining operations and used TCE to remove the cutting oils. The site sits on a thick glacial till with underlying buried valley aquifer and a limestone aquifer beneath that, which is the drinking water source. So that's one advantage is we didn't have a shallow drinking water source. So the release in 1985, there was a catastrophic rupture of an above ground storage tank that released approximately 2,700 kilograms of TCE within a processing room. So this is a zoom into where that tank sat. The TCE flooded the entire process area and entered floor drains and other floor penetrations, and it actually exited the building and ran across the surface of the ground. The initial response was to remove the gross contamination. So anything that was exposed outside, they could easily grab hold of and suck out with vac trucks and those kind of things. And that's what they did. And then they entered a groundwater monitoring program that lasted almost a decade. And by the time a decade was up, the regulators were pushing for some kind of closure because they really hadn't done anything except remove gross contamination associated with the original spill. And this was all done under a consent order. So that's when we were hired. And so we came in and started to evaluate the site and refine the conceptual site model. And we met with the regulators to develop the scope of work for that. We collected high resolution data set using a MIP and 3D soil sampling grid. And then we refined our site drawings. So here's our MIP transects. We had 5 of them from north to south. The northern one, I'll show you the results of, and that's right near the spill area, at least where it came out of the building. We went from north to south because that was what the groundwater flow direction appeared to be from all the groundwater monitoring that had been done. And so if we look at the pre-injection data, MIP data, we do see that there is a strong source characteristic down there around 5 meters or so, and that it extends off to the right there. So what we decided to do was estimate the quantity of TCE that was in the ground based on sampling data that we had that the previous consultant had collected and that we had kind of followed up with. And this is what the concentration looked at like around 3 meters or 1 meter. This was at 2 meters. This was at around 3 to 4 meters. And this was around 7 meters deep. So you can see it went down pretty deep. We refined the site drawings, and what we found was that basically the little stringers of sand that they had monitored as groundwater flow were not connected. So they really didn't understand groundwater flow. All that monitoring that they'd done for that long period of time really wasn't very useful. We also realized that when they put in their wells to do the monitoring, they actually made conduits to drag the contaminants down lower and lower into the subsurface. So there was a lot of issues that just cropped up when we started to look at this in detail. So for remediation, we did a potassium permanganate injection, round 1, followed by soil vapor extraction. And then we did a potassium permanganate flood of the area, followed by more soil vapor extraction. So I'll give you a little feedback on what we did from the injection standpoint and why we went to soil vapor extraction. So here's that MIP transect. We went back out after the first injection and redid the MIP and found that we'd actually pushed the contaminant higher and farther out through injection than we thought. So instead of actually reducing concentrations, we did reduce some, but we actually did end up pushing the contaminant out of the way. So that's something to keep in mind. Then we went in and we decided to do confirmatory sampling locations at the same points over and over again so that we could figure out how our injections had worked. So here's the results of those sampling efforts and injection and followed by soil vapor extraction. And so this is the same area from left to right is the baseline condition, the phase 1 and the end of phase 2. And you see we had some pretty good success in the first meter. Really good success at 2 meters, and then success again as we went deeper to 5 meters and then down around 7. So for mass reduction, because it was easy for us to calculate the mass because we knew how much was released on the day it was released. So we had a good concept of how much mass was in the ground, and we ended up removing about 95% of that mass through the processes we'd undertaken. We assumed that about 500 kilograms was recovered or vaporized during the initial response based on the soil concentrations that we had at the baseline. So of that, 1,000 kilograms was removed through produced liquids. So the soil vapor extraction was actually dual phase extraction, and we removed a lot of liquids from beneath the building. 7,700 kilograms or 770 kilograms were captured vapors. And then we estimated that 225 kilograms were oxidized in place. So closure, we assigned the activity and use limitations. Closure was granted in 2007, and the post-closure care and monitoring period was completed in 5 years later. And what we had to monitor was deeper groundwater to make sure that we hadn't had any contaminants reach that deeper groundwater. We had an intermediate level that we could monitor before the drinking water aquifer, and that one remained clean. So that's how we got our clean closure. So the lessons learned on this one: manage the risks early so it gives you time to assess and consider a lot of different options. Work closely with regulators and your clients to set realistic expectations. Don't promise the world because sometimes you're just not going to be able to make it to that point. Be flexible in choosing remedial technology. So you'll likely have 2 or more technologies that you'll have to use. Document source depletion through multiple sampling episodes. And injections can result in a displacement of your contamination, so be careful of that. The other thing that was important was we learned that you have to sneak up on the source using the MIP. If you go right into an area where you think you have a high concentration, it'll take a long time to get through because the MIP components become contaminated. The other thing that was very useful was we learned that SVE prior to injection helped to dry out the soils and complete a lot of pathways for the injectates. So that's a very good way to approach it. So if you can dry out your soils and remove some liquids firsthand, then the injections don't push them around. And with that, I appreciate your consideration, and I'll be around to answer any questions you may have.
Thank you, Craig, for your excellent presentation, a lot of clarity and a great case study as well. Our next speaker is Dr. Gary A. Burke from Texas Environmental. Gary is founder and managing partner of Texas Environmental based in US, and he's also director of Texas Environmental Limited based in Ireland. Gary is going to present to us on advances in emulsified vegetable oil deployment using in situ alcoholysis. Over to you, Gary.
Oh, thank you for the opportunity today. My presentation today is really on the research and development work we here at Tarsus are doing to improve fatty acid distribution.
I know.
Distribution for enhanced reductive dechlorination. Specifically, what I'm going to present is a co-injection of a three-part system wherein we would use a water miscible vegetable oil, a co-solvent substrate shuttle that dissolves the vegetable oil to create a solution that has distribution properties similar to electron donors, a soluble electron donor rather. And then lastly, a homogeneous alkaline catalyst or alkyl oxides to increase the pH of the aquifer to promote the formation of fatty acids, alkyl esters, carboxylic acid, salts, and lastly, glycerol. So my presentation, there's really in the interest of time, I'm kind of go briefly over 6 items, but what I'm going to really truly focus on is, so when we do injections of and try and re-engineer an ecosystem or an aquifer to promote enhanced reductive dechlorination, that we could potentially have some some side effects. I'm going to review some of those side effects, and then lastly talk about why we're using this 3-part system to overcome some of those side effects. So for enhanced reductive dechlorination, really what we need is an organic substrate that's going to ferment to acetate and hydrogen. We like to use vegetable oil materials or vegetable oil-based products simply because you get a much greater amount of hydrogen per pound of substrate. The soybean oils or vegetable oils will ferment to acetate and hydrogen. It'll give you strong reducing conditions, but you also need to have the right organohalo, respiring bacteria present, nutrients, as well as vitamin B12. So if we look at soybean oil, and it's a triglyceride, so we have 3 fatty acids on a glycerol backbone, and for the most part, it's going to be a C18. And the nomenclature, the 18 or the 16 as shown here, indicates the number of hydrocarbons in the chain. And then the 0, 1, or 2, or 3 rather, would also indicate the number of double bonds in that chain. And so if you look at that, the fatty acids, it's very similar to a surfactant. And that's why we're able to use vegetable oil-based surfactants to help emulsify soybean oil so well. So the way soybean oil or vegetable oils ferment is through a 2-step process. In the first process, the long chain fatty acids are hydrolyzed, and they release free fatty acids and glycerol. So that triglyceride is going to hydrolyze. You'll get 3 moles of fatty acids and a mole of glycerol in the process. And glycerol is very soluble. It easily degrades to trimethylene glycol and then to hydrogen and acetate. And so if we look at the second phase, it's going to be through fatty acid oxidation. And so we have here a head of and that's the carboxylic group. The first hydrocarbon in the chain is the alpha, and the second is the beta. And then the fatty acid oxidation is really a multi-step process where we're going to remove 2 hydrocarbons from the chain. It's going to release 4 atoms of hydrogen and a mole of acetic acid. So what we've actually learned over nearly 2 decades of doing EVO projects is that the distribution of the correct type of fatty acid is really essential. And so through the hydrolysis process, when we generate acetate, the great thing about that, it has a slow consumption. So it's going to stick around for a good period of time. And it will migrate some distance down gradient from the injection point. And the other nice thing, it does stimulate PCE to TCE to cis-DCE. But unfortunately, it will not stimulate cis-DCE to vinyl chloride to ethene. And for that, really, you need hydrogen. And hydrogen is produced through linoleic acid, propionate, butyrate, et cetera. So really, hydrogen is produced from very specific volatile fatty acids. But unfortunately, hydrogen has rapid consumption. And also, it really doesn't migrate beyond the injection zone. So, really that's prompted us to try and create a method where we can increase the production of the correct type of volatile fatty acids, distributed further down gradient, so we can generate hydrogen well beyond the injection zone. And so hydrogen, as is required for cis-DCE to vinyl chloride to ethene. And the other thing that we've learned over the years is that pH really plays a key role in volatile fatty acid production. And more specifically, what we've learned is that systems under alkaline conditions will enhance the activity of a fatty acid producing bacteria. So if you have an alkaline system, generally you're going to see higher VFA production, volatile fatty acids. The other nice thing under alkaline conditions is that what we've experienced and witnessed is that it also inhibits methanogens. And so, so a lot of times you're here, with injecting donors that, we're going to create, high levels of methane. And so we found that by having systems under alkaline conditions, we're going to inhibit those type processes. And we're also going to increase the production of volatile fatty acids. The other issue is that pH also plays a big impact on dechlorination. This is a slide courtesy of serum. But, so really for reductive dechlorination, we want to be between a pH of 6 and 8.5, which a slightly alkaline pH of 7.5 being optimal. And so when we go in and try and re-engineer these systems, so sometimes, often we have sites that are under acidic conditions, or in the process, of reductive dechlorination, we're going to create acids. And through the fermentation of our donors, we're going to create acids. So often, we'll go in and at sites, and when I'm saying often, I'm talking about the community at large, we'll add a base to the system to try and help, increase the pH, from an acidic condition to more to neutral. And really what that process then is known as saponification. And that's the process of making soap. And we, as a society, have been making soap for a very long time. And so to make soap, you need an acid or an oil, a base, for example, that could be like lye, and that's going to generate a soap or a salt. And so when we add a base to an EVO system that's acidic, we really shouldn't be surprised that we're going to generate, potentially some soap scum. And so here's just some photos of some samples that were sent into our surfactant laboratory from various wells that were collected here in the US across the country. And so, we also add nutrients to systems, and the nutrients that are injected within the vicinity of the injection wells are going to also generate excessive biogrowth and further reduce permeability. And then perhaps we have a system where we may have some hard water. And hard water contains salts of calcium and magnesium, principally as like bicarbonates, chlorides, or sulfates. You may also have ferrous iron may also be present. And really what happens in a system where you have injected an electron donor, such as a vegetable type material, the calcium and magnesium ions have the potential to react with the fatty acids that are generated from the hydrolysis process, and they're going to form this insoluble gelatinous crud in the subsurface. And so here's some samples from, I showed you 2 slides ago, some samples of some crud pulled out of a well. And what we've actually discovered, so we have several patents related to surfactants and for DNAPL flushes. And within those systems, we use co-solvents. And we've experimented around with some of those co-solvents. We found that actually liquefies the soap scum. And the interesting thing is the co-solvents will also liquefy the vegetable oils, turning those into more of a system where they can behave as a soluble donor. So with the addition of the co-solvents, we can easily liquefy any gelatinous crud or soap scum material that was created. Here's I'm going to show you a video. This is a bucket. So this was a site where they did groundwater recirculation with an emulsified vegetable oil. And the site had alkaline groundwater and had, really high levels of calcium and magnesium. And you can see in the video, we formed this Vaseline type material that was, plugged up in all of the delivery systems and the wells and the piping. And so they wanted to go in and they reached out to us and to see how we can help them, rectify and clean the situation. And so in our laboratory, we tried again the same co-solvents, and we found that, that the material was very easily liquefied. And so we could liquefy that insoluble gelatinous crud. And then once we added water to that system, we were able to form an EVO. So by flushing out the system with the same co-solvent that we use in some of our sear applications, we can then liquefy those that gelatinous material and then further help distribute in the subsurface. And really from there is where we developed what we call EVS Advanced. And really the goal of this system is to help improve the distribution of the volatile fatty acids, minimize any type of gelatinous crud or soap scum created from pH adjustments in the subsurface, and generally get to the point where we can generate hydrogen well beyond 5 meters downgrading from the injection.
Hi, Gary, you got a few minutes only left.
Okay, and so with the process, this approach really is going to enhance the delivery of vegetable oil-based electron donors. With the substrate shuttle, as I discussed, we're going to optimize, a long-lasting electron donor by liquefying that vegetable oil into very small particles. And this really allows the surfactants to become more efficient and readily perform their function. With the addition of the activator, what we're going to do is we're going to cleave the fatty acids from the triglyceride molecule. And then those cleaved fatty acids attached to the alkyl group, that's the part of the made from the carbon and the hydrogen, are going to attach to the alcohol within the activator to form alkyl, fatty acid alkyl esters, or carboxylic salts, and once again, glycerol. And really then that's just shown here with this animated process right here. And so also we've been doing further research. In addition to the homogeneous alkaline catalyst, we found that we can also activate the system using heat. So, there was a couple of presentations using heat, subsurface heating, I think more specifically thermal resistance heating. So following up onto those processes, while we still have some heat in the subsurface, there's an optimal temperature that we have to be at. So we need to wait a bit for the system to cool, but then we can inject the materials and create this in situ alcoholysis approach. And then we've also been doing some work with enzymes, or more specifically biocatalysts. And so I guess in summary, what we're trying to achieve is an improved method for the distribution of electron donors to produce fatty acids well beyond 5 meters down gradient, and really offer greater transport when we're compared to traditional EVO approaches, and really optimize the system so that we can create hydrogen well beyond 5 meters down gradient. And a typical application rate, I'm showing here. So I do need to interject here. Well, a lot of times we do co-injections with zero valent iron, but actually yesterday we were awarded a patent for suspending ZVI particles in vegetable oils. So likely this is going to change, because in the future, the ZVI will be incorporated into that first step. So where we're talking about using a vegetable oil-based material, and typically these are in situ injection applications where a typical site we would inject it anywhere with, so the in situ concentration would be between 2 and 8 grams per liter of vegetable oil material. And then, if you look at the equation, for every 1 mole of vegetable oil, we need 3 moles of an alcohol. But, that's under ideal conditions, and never those reactions typically ever occur, under ideal conditions. And so typically what we found best is that when we dose at a 16 to 20% of the EVO dose for the activator. And then for the co-solvent, typically application rates for that's going to be upwards of about 0.4 grams per liter. And then, like I mentioned earlier, we've had great success when we also used zero valence iron as a co-injection with the process, and that would be anywhere between 4 and 6 grams per liter. We at Tersus have been working with PLM equipments out of Messy, France, for well over a decade. And even prior to starting Tersus, the principals at Tersus had a relationship with Nico at PLM, and so we actually now blend, warehouse, and stock products in Messy, France. And also, I should mention for the EU market, we source vegetable oils locally within EU, and all our surfactants, the components for the systems are procured from surfactant manufacturers based in the EU. We at Tersus have a variety of products, and with that, my contact information as well as Nico's with PLM. And thank you. And we certainly do really appreciate the opportunity to present today.
Thank you very much, Jerry, for your excellent presentation. Lots of information in there. I would like to move forward now with our last speaker today, Johan Fausto Ortiz Medina. Fausto is a research associate working at EOS remediation, and his main responsibility being to conduct research and develop new technologies for in situ bioremediation. The title of his presentation is The Importance of pH Control and Nutrient Amendments to Achieve Optimal Enhanced Reductive Dechlorination. Please join me in welcoming Johan Fausto. Over to you, Johan.
Yes, thank you, Ravi. Can everyone hear me? Yes. Okay, so I will try to make it quick. So yes, thank you everyone for attending this conference. It's been a pleasure to be here again at Remtech Europe. I will talk about the importance of pH control in bioremediation, specifically to remove chlorinated compounds. So just as a bit of information about myself, as Ravi said, I'm a research associate working at EOS, and my main area of expertise is environmental microbiology and biotechnology. So that's my main area to contribute to the field of bioremediation or remediation in general. In case you are not familiar with our company, we are based in North Carolina in the USA, and we are one of the leading companies in bioremediation. In fact, we are the original developers of the emulsified oil technology. And we have also a wide array of products to remediate contaminated sites through bioremediation. We have been operating in the European Union since 2010 through QM Environmental. In fact, there is a stand by them at Ferrara, so you may want to stop by and learn more about the solutions for your contaminated sites. So the reason why we advocate for bioremediation is because by using bacteria to eat all the contaminated compounds, or well, the contaminated compounds, in a long-lasting and sustainable way. In fact, when compared to other treatments, for example, chemical oxidation, enhanced bioremediation doesn't offer any rebound. That means that once the bacteria eat a contaminant, it's gone for good. And this is true especially for chlorinated compounds. The main focus is definitely, as the session implies, the chlorination. So in this case for bioremediation, through the process called enhanced reductive dechlorination, The bacteria, by providing some substrates, will remove some chlorine compounds from highly chlorinated compounds, such as PCE or TCE, and in the end generates non-toxic compounds such as ethene. We can see this process to be separated in two stages, where from PCE to DCE there are multiple organisms involved that they can utilize acetate or hydrogen, and in general they are more flexible. However, from DCE to ethene, there is only one highly known microorganism involved, the Halococoides McCarthy. This bacteria grows in more strict conditions because it grows slowly. It only accepts hydrogen as a substrate, and that is generated through fermentation of other substrates such as vegetable oil. And it requires some other nutrients such as ammonium or nitrogen and vitamin B12. However, the title of the presentation is the importance of the pH, and that is the reason why we'll explain that pH is important for this chlorination. In fact, from the first stage from PCE to DCE, the process is more flexible, as I said, and the pH is optimal at 7. And as the process goes down, there is sometimes an initial inhibition, as you can see here in this graph, but complete conversion is still possible. Once this lag phase is over, in most of the cases, the chlorination rates recover. On the other hand, from the DCE to ethene, the Halococoides process, even though the pH is optimal at around 7 as well, once the pH goes down, you will start seeing some inhibition. And as the pH goes lower, the inhibition gets stronger. So sometimes just because of a low pH, you will see phenomena such as a stall of DCE. So basically your process is halfway done and it stays there. And this is the reason why pH is so important to be controlled and monitored. Now let's discuss the sources of low pH. And the first one is naturally the pH of the environment. We can see in this map of Europe that some regions, for example, the Mediterranean, has more, neutral to alkaline soils. So it's not a big issue. But if you compare, for example, regions such as the Nordic countries, UK, etc., the pH is lower. So it is very likely that in these regions, the Halococoides is not thriving. Therefore, some strategies, for example, adding that culture through bioaugmentation, and definitely proper pH control is needed. So this is something to consider here. The second cause of low pH is, as we discussed before, the acid production through ERD. We can see in the chlorination process that every time you move along the process, you remove some chlorine atoms, but you're also generating a proton here. So therefore, by consumption of hydrogen, you are basically generating hydrochloric acid. That means that the protons will be added to the aquifer and the pH will inevitably go down. This is not a big issue in terms of molar perspective. However, if you have a big plume, for example, at DNAPL, you will start seeing that the pH goes down just as the chlorination process moves on, and that will eventually interfere with the chlorination process. The third cause of low pH is substrate utilization. As we saw before, bacteria need a substrate or basically foods to perform this process. But we also need to consider that besides hydrogen being generated, all these fermentable products will generate by their consumption some amount of carbonic acid or carbon dioxide. This is quite important because as it reacts with hydrogen, some protons will be produced as well. And the extent of the proton production will depend on the pH itself. Therefore, if you have around pH around 7, you will have some alpha values as detailed in this equation. That's basically will tell you that several protons will be produced, and the higher the pH, the more protons you will produce, and the equilibrium will shift towards the left. Therefore, this is something necessary to consider, that as the food goes consumed, your pH will go down as well. The impact of the proton production will depend on several factors, among them the aquifer buffering capacity. And this is important because in many sites, you will not notice the decrease in pH at first. And one of the main reasons is because you have some minerals, for example, calcium carbonate dissolved there. Calcium carbonate will capture the protons there and basically neutralize the pH under some points. But we need to remember that this is only effective as calcium carbonate is dissolving. We can see in the previous slides that the fermentation of the substrates also generate CO2. So there will be a point where the groundwater will become saturated with carbonic acid and with the carbonate system. So calcium carbonate will not dissolve anymore. Therefore, incoming protons may not be absorbed by the system and the pH will go down inevitably, therefore requiring, in the end, some sort of proper pH control. So how can we control the pH? We can add either a base or a buffer to adjust the pH. Here I'm showing you some of the most commonly used bases here. Some of them, well, all of them have their own advantages and disadvantages. For example, sodium hydroxide is quite soluble, and you can say that it's quite cheap to obtain. However, if you inject it, there is a possibility of overshooting, basically having a pH higher than what you want, and that will definitely kill the bacteria. There are some limitations, for example, with the carbon-based buffers as well, because they are dependent also on the carbonate system. And for example, brucides, the main limitation is the solubility, but you can have some more amenable pH in the end. And we need to remember as well that the amount of base needed will depend on the initial pH and also on the acidity of the system. The dissolved species that makes up the acidity of the system will tell you in the end if you need more base than expected to equilibrate the pH of the aquifer. So here at the EOS remediation, we developed another set of buffer called COBOF to increase and stabilize the pH. What COBOF is a colloidal suspension of magnesium hydroxide, which when injected in the system, it will stay in the soluble form, and the solubility will be controlled by the pH of the system. Therefore, at higher pH will stay in the solid form, but as the pH goes down, as we can see in this graph, it will dissociate into magnesium ions, but more importantly, into hydroxide ions that will neutralize the system. Here we show you a little study where we injected COBOF, and you can see that the initial aquifer of the initial pH of the aquifer of the site was a little bit below 5. But as COBOF was injected, it will eventually stabilize the pH to a more amenable value here, and it will stay like that for over a year and from quite a high distance from the injection well. So now we can show what wonders the pH control does when treated chlorinated compounds. Here we show you a site in the US. It was a quite challenging site here that had a quite high concentration of chlorinated compounds, over 7,000 micrograms per liter. One of the challenges here is that the pH was quite low initially. And one of the reasons why it was so low, besides of the natural pH of the site, is because there was a sulfuric acid plume entering from the northeast. So basically, you can tell that's how it's affecting the site, because you can see some high concentration of sulfates as well, besides the pH. And naturally, no dihalocopoides were detected on these sites. Therefore, in order to treat this site in an affordable way, some biomimetation had to be performed. And this is the process that was performed. As I said, some dihalocopoides culture was added, along with some emulsified oil and a small amount of COBOF. This was 10 years ago, so we were not sure how many COBOF was needed to inject. And after injection, there was a rapid conversion of PC to DC, as you can see in these graphs. It decreased quite considerably during the first years. And this was partly due to a gradual pH increase, which promoted better conditions for the bacteria to grow. However, we can see that there was a little bit of stall of DC and vinyl chlorides. So they were not decreasing after this time, and this was one of the challenges of this site. To remediate this, we performed a pilot test where we found that some nutrients such as nitrogen were needed, and also a higher need for pH control. Therefore, in this case, we needed to inject, or we injected some EOS Pro, which is our flagship emulsified oil with nutrients added, and a higher amount of COBOF that accounted all of these factors in the sites. And you can see after the second injection that the stall was overcome, the DC and BC decreased, and finally some ethylene was produced. Therefore, the sites achieve a closer step towards completion. As I said, it's a very challenging site, but we overcome the main challenges here. So what I want you to learn from this presentation is basically how important is pH towards achieving optimal bioremediation. We can see that even not so low values such as 6.3 will affect the process of DC to a thin. And as I mentioned, there are several causes of decreasing pH, so we must need to always take care of pH and monitoring it. And we can solve some of these issues by adding a buffer and base. The amounts needed will depend on the aquifer acidity and buffering capacity. And EOS remediation and QM will definitely back you up with the science and enough technical expertise to calculate the proper pH control. So, well, just if I have a little time, there is just a base addition tool that we have at EOS remediation. So in case you want to estimate how much base you need, you can consult us. And here's my information and my colleagues, so you can reach out to us as well. Thank you so much.
Thank you very much, Yuan, for your excellent presentation, the importance of pH and additives in conducting remediation. So we're now into panel session, and I'll step back and have Frank take over chairmanship of the panel session.
Thank you very much, Ravi, and thank you to all the 7 speakers. I think it was really an excellent session, and I learned a lot here, very educational. We have a little problem. We only have 2 official minutes left for the discussion, and we have quite some questions on the chat. What I'd like to propose is the following. I really would like to hear you all speakers answering one question and the same question. And that is about in all remediation technologies of chlorinated compounds, we have this problem of the daughter compounds, not at least phenyl chloride. So I would propose to ask all the speakers, beginning with Mariangela, to expound a little bit on that. How did you deal with your in situ sorption and IRCR procedure? How did you deal with daughter compounds in your projects? Could you maybe tell a little bit about that, Maria Angela?
Yeah. Yeah, well, in our project, the reactant that we foresaw could treat also the daughter compounds. So the activated carbon and the zero valent iron had more efficiency, it acted more rapidly on the parent compounds, but also the daughter compounds were sorbed to the activated carbon, and the activated carbon plus the zero valent iron could also, well, in specific, the zero valent iron allowed to block the formation of daughter compound because, well, there were already some daughter compounds in the site we saw, but the zero valent iron allowed to have a beta elimination process that allows to skip some phases to daughter compounds. So we treat the daughter compound presence and we reduce the formation of new compounds with the zero valent iron.
Okay, thanks a lot, Mariangela. Pierrot, did you recognize the problem of the formation of dotted compounds, and how, if yes, how did you deal with it in the electrical resistant heating procedure?
Yes, the technology does not produce dotted compounds, but anyway, they were already present because of degradation that was already present at the site. So we didn't induce any problem related to dotted compounds, but we had to manage in terms of effluent treatment, the presence, the significant presence of vinyl chloride. So the only point was to put a module, a dedicated module, because activated carbons are not so efficient in treating vinyl chlorides. We added a dedicated module for treating, effectively treating vinyl chloride. That's the only point, because otherwise the technology doesn't cause dotted compounds.
Does it mean, Pierrot, that the procedure that it destroys all compounds, including vinyl chloride?
Yes, you remove it because you remove it through volatilization. So you don't destroy them on site, but you remove it through the extraction system.
Okay, that's good. Follower, you're still present, I see, yes. About the DNAPL dissolution. Did you take in particular care for the dotted compounds like vinyl chloride? Was it an issue in your projects? And if yes, how did you deal with it? You are muted at the moment.
Okay, all right. So
That's
since
better.
the site on which I'm working is really an industrial site, and downstream this site we have some captage of drinking water. And so, of course, the problem about the daughter product is very important because they are more dangerous than even the primary ones. So we really take care of that, but I don't really deal with it. We just use them as an indicator of the pathway of degradation. For example, to know which pathway really is occurring, and knowing it is really important of having the right kinetics to apply to the models.
But you did follow the pathways of the different components, the different molecules. Did you specifically take into account the more toxic compounds like vinyl chloride?
We have the daughter product that we had is the DCA, the dichloroethane. So since the groundwater condition, geochemical condition are aerobic, there is no further degradation of DCA. So basically everything stopped there. But this is dangerous, of course, and this is why we take care of that and try to see, to do the model and see if the concentration is going to grow or not.
Okay, thanks, follower. Mike, yes. I think, I'm not sure if you mentioned daughter products in your presentation, but I think closure, you have to deal with the daughter compounds in your procedure, right?
Well, somewhat similar to the remarks that Mr. Mori made, when there's a successful ISCO event, ISCO process, there are no intermediates produced. The monitoring, I believe, though, I think maybe Mr. Optum's on the call, but the monitoring that the contractor performed, I presume, was for not just the primary contaminant of concern, but for the intermediates. I'll arrow through there, but typically, no, we don't see that reproduction of the.
But you mentioned the word successful ISCO,
Yes.
Generally, you focused on the disappearance of PCA, TCA. Do you also look at if the ISCO is successful in the respect of the daughter compounds?
Yes, typically a monitoring program would look for that. And if there wasn't enough contact with sufficient amount of, in this case, persulfate or another oxidant for a sufficiently long amount of time, then it is possible that the primary contaminant is not. Sorry. Go ahead. Yeah. Sorry, I was distracted for a second.
Okay. Good. Thanks, Mike. Correct closure of the DNAPL. Was the phenylchloride an issue here?
No, at this site it wasn't. But again, if it's an ISCO situation, we basically use two technology of physical extraction. So we just extracted the material from the earth as either vapors or liquids. And then ISCO, mineralizes the contaminant in place so it doesn't produce the daughter products. We eventually did do vapor intrusion evaluations at the end. And that part, we did look for vinyl chloride, but didn't see any. So I think we were very successful in remediating, and we didn't really have a vapor intrusion issue at the end.
So except for the theory, you did also monitor it, you checked it?
Yes, yes.
Okay, okay, that sounds good. Finally, Gary, the EVO destroyment, you have to deal with the daughter compounds.
Yes, and in the interest of time, I could have I didn't have but 15 minutes, so I wasn't able to present a case study. But as I mentioned that in that one slide towards the end, we also co-inject with zero valent iron for the abiotic processes, which was also previously mentioned. And then we will also add a biological culture to deal with the daughter compounds. For example, KB1 from serum, and that culture actually has the VC reductase gene in it, so it will degrade those daughter compounds.
Okay. Sounds good. Sounds good. I said finally, but we still have Fausto. Fausto, same question for you. The enhanced reductive dechlorination. You also have the problem of the daughter compounds, I believe.
Yes, I will not call it a problem per se, because in the end, that's part of the process itself. You see that, as I explained it, it occurs in two stages. So the first one, until DC, is not usually a problem. Sometimes you accumulate the DC. But as I show in this case, the process was about 7 years ago. I mean, this site that we were treating, it's almost 10 years. And we learned a lot of it, of DC stall and how to solve it. So therefore, when you find some daughter compounds as DCE and BCE, is it's not the end of the world. Basically, I mean, up to this point, we have developed in the bioremediation process several solutions to solve it. And once it's solved, as I illustrated in that case, both of them go really, I mean, they go down and some ethylene is produced in the end.
But why do you say it's not the end of the world? You can worsen your situation when you eliminate PCEs, TCEs, and you end up with phenylchloride.
Exactly, yes, but it's not something that is not unsolvable. That's what I wanted to say. So, okay. And I said at this point, as I illustrated, we have several solutions, such as adding nutrients, optimizing the pH of the system, because there are many causes of that, but they are solved.
Okay, thanks, Fausto. I look at my co-chairs. I'm not sure if Christiane is not still there, but Ravi is. Do you have anything to add or a final question, Ravi or Christiane?
The only question
yes.
The only question that I have, Frank, and this is from Australian perspective, groundwater composition can vary quite a lot. You could have very hard water as well. And therefore, the application of some of the strategies that we have heard today, how effective would these be, particularly if you end up with hard water?
Anybody like to respond? One of the speakers? Does not seem to be the case, so I'm afraid you have to put this question to the conference next year in Australia, Ravi, cleanup conference.
We'll certainly do that, and indeed, Cleanup 2022 is in September, and we're looking at hybrid session as well, and that's in Adelaide. So we look forward to all the participants who could join us there.
Okay, ladies and gentlemen, thank you very much for being present. I enjoyed the session very much. Sorry that we are 11 minutes late, but I think it was nice to have some discussion at least. Thank you very much, everybody, especially the 7 speakers of today and also all participants. Enjoy the rest of Remtech and have a very good afternoon, evening, morning, whatever. Goodbye.
Thank you. Bye-bye.
Bye-bye.
Thank you.
Frank, before ending, please show the general timetable of Remtech Europe.
Oh yeah.
Okay. And just a moment, I will put also a message, an important message into the chat. Just a moment.
Sure.
I will try to post it. For who wants the certificate of attendance, just a moment, I will send you a link, Google form, where you have to put to inscribe to have the certificate of attendance. Just a moment, I will question of 1 minute for who is interested, of course, and not all the others. Okay. Not to just to Frank, but to all. Okay. So for having the certificate, you have to register here in this Google form. If you have already done, you will receive them. For the program, do you have it at hand, Frank, or you prefer I will share it?
I'm not sure if I have it. No, I don't have it available, Michael. Sorry.
Don't worry. I will end it. Just a moment. I have to go in the right place. Okay. I will share the screen. Just a moment. Share screen. Okay. Okay. I hope you are able, Frank, to see my general program. Okay. So we are in Wednesday 22. We have starting from 2:30 p.m. Central European Summer Time, and then you can check your favorite time zone. The training from the U.S. Department of Defense, SERP, and STCP with current approaches for vapor intrusion, site investigation, and mitigation with also Frank, that will be chair of this session. I know, Frank, it's the topic where you are passionate, right?
Exactly.
Okay.
Right.
Then if you like to switch into sustainability, there is as you can see from the first column, the webinar from Rumble on sustainability assessment for a more sustainable remediation, targeting soil and sediments. And then the most crowded event, I'm sorry that it's too late for Ravi for joining, on PFAS remediating the forever chemical. And so I will ask if you are interested to join us in our platform, remtech.matters.space. We will circulate to people that are already registered in the Google form also the Zoom link after 2 minutes after each webinar will have been started. Okay, that's all from my side. So I hand out again the floor to Frank, Ravi, and Christian for the closing.
Yeah, we already started the closing procedure, actually. I thank everybody again, especially the speakers and all 100+ participants. Have a very good continuation of the REMTech Congress. See you later. Bye-bye.
Bye-bye. Bye-bye.
Bye.
Thank you. Bye.